We are in section 9.2, two means, independent samples. In this test, we collect two independent samples to test whether there is a difference in means between two populations, or if one population mean is greater or less than the other. Comparing SAT scores between men and women is an example of a two independent sample test. Sampling distribution of the difference of two means, independent samples with a population standard deviation unknown. This is using Welch's T. Suppose that a simple random sample of size n1 is taken from a population with an unknown mean mu1 and an unknown standard deviation sigma 1. In addition, a simple random sample of size n2 is taken from a population with unknown mean mu2 and an unknown standard deviation sigma 2. If the two populations are normally distributed or the sample sizes are sufficiently large, which we say is greater than 30, then our t distribution, our t statistic, can be calculated with the following formula. And it approximately follows a student t distribution with the smaller of n1 minus 1 or n2 minus 1 degrees of freedom, where x1 bar is the sample mean and s1 is the sample standard deviation from population 1, and likewise for population 2. The box right underneath this says testing hypotheses regarding the differences of two means with the TI-83 or 84 calculator. So we can use the following steps, provided that we would have to check these. Both have to be simple random samples. The two samples are independent, and the differences are normally distributed with no outliers, or the sample size is sufficiently large, greater than 30 for both of our samples. Step 1 would be determine the null and alternative hypotheses. The hypothesis can be constructed one of three ways. If you notice, your null is saying that the mu's are equal to one another for each sample, the means would be, and our alternative depends on if it's a two-tailed, left-tailed, or right-tailed test. Step 2 is to select our level of significance, or alpha, and again, that's usually given to you. Step 3, we're going to go to stat, test into number 4, which is 2-samp t-test. If data is raw, input the data into L1 and L2. And your frequency list needs to be set to 1. If summary stats are known, enter in all those summary statistics. Highlight the appropriate relationship between mu1 and mu2. Set pool to no, and highlight calculate. The calculator is going to give you t, which is your test statistic, and p, what is your p-value. And step 4 is going to be if the p-value is less than alpha, we reject H naught, and then we're going to have to state our conclusion, just like how we've been doing this entire semester. On the next page, we have constructing a confidence interval for the differences of two means with the TI-83 or 84 calculator. Step 1, we're going to go to stat, test, and go down to 0, which is 2-samp t int. And again, if the data is raw, we are going to input those values into L1 and L2. Frequency is set to 1, and if summary statistics are known, we input all those values in. Pooled needs to be set to no, and we select our confidence level. The calculator is going to give you your lower bound and your upper bound, just like what we saw in Chapter 7. The example says, assume that the populations are normally distributed. We have population 1 and population 2, with the sample size, the sample mean, and the sample standard deviation given. Part A says to test whether mu1 is not equal to mu2 at the alpha equals 0.05 level of significance for the given simple sample data. And so in order to do this, we need to come up with our null and alternative hypotheses. So H naught and H1. Since we know what we're testing, go ahead and put that in. And then your null is going to be that they are equal to one another. In order to do this, we need to use our calculator. On your calculator, you're going to go to stat, to test, on your calculator, you're going to go to stat, to test, to 2-samp t-test, and we are dealing with statistics. And so we have x bar 1 is 111. Standard deviation for our first one is 8.6. And our sample size is 20. X bar for 2 is 104. Standard deviation is 9.2. And our sample for the second one is 20 also. Your alternative hypothesis is not equal to. Again, set pooled to no and hit calculate. Again, we get T, which is our test statistic. And we also get our p-value. From the calculator, we get a p-value equal to 0.0175, which is less than alpha, which for this problem is 0.05, which means that we are going to reject H naught. And go ahead and write a little star over here, and I want you guys to try to write your conclusion on your own, and we will talk about it in class. Part B says to construct a confidence interval appropriate for the hypothesis test in part A. So in order to do this, we're going to go ahead and sketch our normal curve. And since we're dealing with a two-tailed test, that means that my alpha value gets split up in each tail. So each of these tails is going to have alpha divided by 2. And each of those is going to be 0.025, since alpha is 0.05. And then that means that your confidence level, your C level, which is the part in the middle, is going to be equal to 0.95. So we're going to need to use our calculator to come up with our confidence interval. On your calculator, go to Stat, Test, 2SAMP_T_INT. We are dealing with statistics. Put all your numbers in. Your confidence level on this one is 95%. Again, pooled is no, and then calculate. And you get your lower bound and your upper bound. From the calculator, we get a lower bound of 1.298 and an upper bound of 12.702. And again, this is where we check to see if 0 is in that interval and 0 is not in the interval. Since 0 is not in the interval, that means that we are going to reject H naught. The next example, it's a little bit more of a word problem here. This one says that researchers from the University of British Columbia conducted a study to investigate the effects on color on cognitive tasks. Words were displayed in computer screens with a background color of red and blue. Results from the scores on a test of word recall are given below. Higher scores correspond to greater word recall. So there's the red background and the blue background, and our sample size, our mean for each sample, and our standard deviation for each sample are given. Part A says to use a 0.05 significance level to test the claim that the samples are from a population with the same means. Assume that the criteria has been met to perform the test. So first thing we need to do is we need to set up our null and our alternative hypotheses. So H naught and H1. So it's asking to test the claim that the samples are from populations with the same mean. So that means our null and our alternative are talking about means. We have two sets of data. And I'm going to go ahead and put not equals to. And equals to, again, is always for my null. Not equal to because it's testing to see if they're the same. And so the opposite of that would be not equal to. So we need to use our calculator. On your calculator, you are going to go to Stat, to Test, down to 2SAMP_T_test. And we are dealing with statistics, so we're going to go ahead and go over to statistics. And we're going to put in all of our information. We know that X1 bar is 15.89. X1 is 5.9. Our first sample size is 35. For our second set of data, the blue background, X bar is 12.31. Our standard deviation is 5.48. And our sample size is 36. Our alternative hypothesis is not equal to, pooled is set to no. And down to calculate, select enter. And you guys are going to get your T value, which is your test statistic, and P, which is your P value. From the calculator, we get a P value equal to 0.0101, which is less than alpha, which is equal to 0.05, which means we are going to reject our null hypothesis. So from here we need to write a conclusion. So in conclusion, there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean word recall is different for red and blue backgrounds. Part B says to construct a confidence interval appropriate for the hypothesis test in Part A. What is it about the confidence interval that causes us to reach the same conclusion from Part A? So first thing we're going to do is we're going to go ahead and sketch our bell-shaped curve. And since we're dealing with a two-tailed test, we're going to go ahead and put those two tails on there. Our alpha level is 0.05, so again, we're going to take that 0.05 and it gets split into each of these tails because it is a two-tailed test, which is going to be 0.025. And that means that 95% is left in the middle. And so we need to use our calculator and get our confidence interval. On your calculator, you're going to go to Stat, to Test, down to 2samp T int, and we have statistics. You need to put all your values in. They should have transferred right over. Our confidence level, though, is 0.95. Pooled needs to be set to no, and calculate, enter. We get our lower and our upper bound. From the calculator, we get a lower bound of 0.882 and an upper bound of 6.278. And again, we need to look to see if 0 is in the interval, and 0 is not in the interval. And so this means that we are going to reject H0. And so again, your conclusions are going to be the same regardless of if you do the confidence interval approach or that p-value approach or even that traditional approach that we have too. So the values there are both reject H0 for both of these. The conclusion that could be written for this is the same that is typed up above. The next example, we're going to go ahead and circle and we'll work on that one together in class. And then we're in the next section, which is 9.3. This is two dependent samples or matched pairs. And it says inferences on matched pairs data is very similar to inferences regarding a population mean. So the first thing that we have is testing hypotheses regarding the differences of two means using a matched pairs design with a TI-83 or 84 calculator. So we can use the following steps provided that. So again, checking to make sure we can actually perform our test. We have to have both simple random samples. The sample data is going to be matched pairs, so that dependent sampling. Differences are normally distributed with no outliers, or the sample size is large, say greater than 30. Step 2 is the null and alternative. So since these are matched pairs, we're able to subtract those values, and that difference is going to have some kind of meaning in it. So we can subtract those values, and we'll say that if there's no difference between those values, maybe you're before taking a study class and then you're after taking the study class how you would do it on an exam. And if you subtract and get 0, that would mean that that study class had no effect on your grade. And so if you notice, your nulls are going to be mu sub d for all of these, and they're always equal to 0, and that would mean that there's no difference between your data that is getting matched up to one another. And then H1 depends on, again, what it's talking about in the problem. So mu sub d is the population mean difference of the matched pairs data. Step 2 is select alpha, which again is usually given to you. And then since we subtracted our values, and we have a difference now, we just have one list of numbers. And so it's actually what we used in the previous chapter, and we'll just be using t-test. So mu sub 0 is going to be 0. X bar we'll put in as mu sub d, and S of x is going to be sigma sub d. And the calculator is going to give us the t, which is our test statistic, and p, which is our p-value. If the p-value is less than alpha, then we reject h0, state our conclusion. It also says that if the sample is small, we say greater than or equal to 30, construct a normal quantile plot and box plot to verify the differences come from a population that's approximately normally distributed. Second box that we have down here is the confidence intervals for matched pairs data with a TI-83 or 84 calculator. The interval is exact when the population is normally distributed and approximately correct for non-normal populations, provided that n is large. A confidence interval for mu sub d is given by, we're going to use t interval, and again it's going to be given as the lower bound and that upper bound. So the next example that we have, in an experiment conducted online at the University of Mississippi, study participants are asked to react to a stimulus. In one experiment, the participant must press a key on seeing a blue screen. Reaction time in seconds to press the key is measured. The same person is then asked to press a key on seeing a red screen, again with reaction times measured. The results for the 6 randomly sampled study participants are as followed. Note: a normal probability plot and a box plot of the data indicate that the differences are approximately normally distributed with no outliers. That's in there because our sample is small. We only have 6 participants, and so we need to know that it's coming from a population that's approximately normally distributed. So, same person is asked to perform a task twice. So we know that we have participant 1. Their time to react to the blue screen was 0.582, and red is 0.408. We can subtract these, and it makes sense to us. For this problem, we are going to do blue minus red. So I suggest writing that down how you plan to subtract whenever you have this dependent or this matched pair data. And the reason why is because just so you don't accidentally start subtracting the opposite way, it's going to mess up the signs and it will lead to a different answer if you do it not for the entire problem. So subtracting this, I'm going to get 0.174. I get 0.074. We get 0.299. I get negative 0.135. And I get 0.229 and negative 0.083. So again, double check, make sure you can subtract those and you get the same value. It doesn't matter the order that you subtract if you wanted to do red minus blue. The signs are going to be all different, but your conclusion with your testing will be the same. So on the next page, it asks for why are these matched pairs data, and the reason why is because it's the same person being tested for both the red and the blue stimulus. So it's same person, so same person for both tests. Part B says, in this study, the color that the student was first asked to react to was randomly selected. Why is this a good idea in this experiment? This allows for you to control any type of learning that might go on. So I understand that they're pressing a key, but at first you're going to not be moving quite so fast, but the more practice that you have, you're going to start picking up speed and your reaction time is going to be quicker. So this isn't a control any learning for this game or this study. Part C, asks, is reaction time to the blue stimulus different from the reaction time to the red stimulus at the alpha equals 0.01 level of significance? So this is asking us to perform a test. So in order to perform a test, you always need to write down your null and alternative hypotheses. So H0 and H1. Since we subtracted those values because we had matched pairs data, we're going to use mu sub d. Our null is always that it's equal to 0, which would mean that there's no difference in reaction time between that red and blue stimulus. And so our alternative hypothesis is going to be that there is some kind of difference, so that would not be equal to 0. So we need to use our calculator in order to do this. On your calculator, you're going to go to Stat, Edit, enter in those differences into L1, and then you're going to go to Stat, Test, and we're going to go down to our t-test. And we are dealing with data. Mu naught is going to be 0. Our numbers are listed in L1, frequency is L1, and our alternative hypothesis is not equal to. Go down to Calculate, select Enter. T is our test statistic, and P is our p-value. From the calculator, we get a p-value equal to 0.2466. And this is greater than alpha, and alpha for this problem is 0.05. And this means that we do not reject H0. So we need to write a conclusion based upon our findings. So in conclusion, there is not sufficient evidence at the alpha equals 0.05 level of significance to conclude that there is a difference in the reaction time to the red and blue stimuli. Part D says construct a 99% confidence interval about the population mean difference. Interpret your results. So first thing we're going to do is that this wants us to draw a 99% confidence interval. So sketch your bell-shaped curve. 99% is going to go in that middle. So 0.99. So that is our C level is equal to 0.99. And so we need to use our calculator. We're going to go to Stat, go to Test, go down to T interval. We are dealing with data. Again, our numbers are in L1, frequency is set to 1, and our confidence level this time is going to be 99. Calculate. We get our lower bound and our upper bound. From the calculator, we get a lower bound of negative 0.379 and an upper bound of 0.193. And since 0 is in the interval, since one is positive and one is negative, that means that we do not reject H0. The next example that is on here, we will circle and we will work on that one together in class.